Puzzles 2017.
Okay, before start, a brief introduction about us. I'm Andrea Allievi. I'm a security researcher and security research engineer of Microsoft now. I have worked for 3 years for the Cisco Talos team, and I'm specialized in Windows internal and low-level reverse engineering. I have previously worked for Prevex, Webroot, and SaferBets that are companies and located, even one is in Italy. I am the original designer of the first UEFI bootkit in the year 2012 and the first patchguard 8.1 bypass presented in the year 2014. And I'm one of the designer of the Windows PT driver that we are going to present.
And I'm Richard Johnson. I'm the research technical lead for Cisco Talos. We have a team that does vulnerability research, and I help guide those efforts. You may have seen some of our vulnerabilities in the past year. And we focus on technologies mostly for finding bugs. And so this was, as he mentioned, some of my talks the last couple of years at Recon have been in the focus of high performance applied to fuzzing and engineering technologies that give us feedback-driven fuzzing and componentizes the different parts of the process to try to make it as fast as possible. I came across this new architectural feature in Intel CPUs called Intel Processor Trace about 2 years ago, and basically it's a hardware-supported mechanism for doing code coverage. And I made a prototype for this in 2015 that worked for Linux because there was experimental support via some open source drivers. And after evaluating it, I realized that this would be a great thing to bring to the Windows operating system, but the Intel support for it was not going to be suitable for what we were looking for. So last year at Recon, we had our very first version of the Windows driver working like an hour before we got on stage, and it was doing a raw decode. And so we're going to talk about the last 6 months of developments, which have brought all kinds of support to the driver, and this picks up where the last one went off. So Andrea is going to give you the introduction of the technical details of the driver and the low-level implementation and some demos, and then we'll address that as applied to fuzzing and finding bugs.
Okay, speaking about processor trace. The processor trace is a new feature of the latest Intel Skylake CPU. It's very useful because it can trace whatever your CPU is going to execute, like in hardware, and it has some particular benefit, especially for code coverage, for dynamic code coverage. For example, if you would like to understand what a particular piece of software would like to do, for malware analysis or for whatever. I mean, the usage are various. For I would like because we have not a lot of time, I would like to be quite fast in describing how is the Intel PT is executed in a CPU, and I would like to concentrate on the new feature of our driver. Basically, being fast, to discover the Intel processor trace in a CPU, you can do even in a user mode, only emitting two CPU ID instruction with two different leaves. One, it's used to detect the support for Intel processor trace. The second one is used to detect the feature of processor trace, because different CPU can implement different features. Processor trace has been implemented in the first time in Broadwell architectures, but it was limited. Now in Skylake there is the full support, and you can trace whatever you would like. The Xeon CPU will be released by Intel in the second quarter of 2017. They are quite done. Okay, here in this slide I would like to show the code for detecting processor trace. As you can see, it's quite easy, and there's nothing special, only a pair of CPU ID instructions. Okay, let's speaking about why is so interesting. It's because it's implemented entirely in hardware. One of the basic things that we can say about this is that it's not detectable by software. I mean, in user mode software. And one important thing to say is that you can trace whatever you want, even SMI, SMM handler, and even an hypervisor code or whatever. The only things that you can't trace is like the SZX secure container, but it's a good thing because the SZX by design should work in an isolated environment. Okay, even here, quite fast, how it works. The processor traces works in three modes. It can trace using three different kinds of filtering. The first is by current privilege level. I mean, you can differentiate between kernel mode software and user mode software. The second filtering mode is by PML4 page table. In that way, you can trace only a single process, because you can instruct the processor trace to trace only a specific PML physical address page table. In that way, you can trace only a single process. Otherwise, the last filtering mode is by instruction pointer. You can set a start point and an end point, and ask the processor trace to trace only that window of code. And this is very cool. The output logging is done directly in memory, in physical memory. That's why we need a driver to manage that. And the logging could be implemented in two ways. The first one is single range. There is a circular buffer, and the trace is written always in the same place in memory. The second type is the table of physical address, also known as TOPA. Okay, even here, like quite fast. To implement the single range, you should allocate a continuous physical memory buffer, and then you should set two proper model-specific registers. One is the RT high T output base and the output mask. And then you have to start the trace, setting the trace EN flag in the control the register. The buffer is automatically filled in a circular manner by the CPU. The table of physical address. The table of physical addresses is a better implementation of the output, because you can set various physical memory address, and you can create like a table in which you instruct the CPU where to write exactly in memory. It's very smart, because you can even set a PMI interrupt that is raised by the CPU if a certain part of the buffer is filled by the log. And then you can stop, you can resume, you can do whatever you want. Okay, different kind of packets. To log the software execution, processor trace uses a different kind of trace packet. There are a lot of timing packets that we are not interested to. The packets that we are interested to are the branch packet, the taken, not taken, the target AP, and flow update packets. There are those packets are the most interesting, because with those you can trace the execution of the software and follow its execution, even maybe checking the source, the assembly code. Here is a big diagram. I will refer you to the Intel manual if you would like to understand the nitty-gritty details of each packets. The one that we, as I have said, the one that we are interested in are the branch packets. Taken, not taken, target IP, and flow update. Okay, let's speak about the Intel PT driver implementation. Okay, we have decided to write this driver to be able to perform the trace directly from a Windows operating system. At this time of this presentation, the driver is quite stable, and in its version 0.5. It supports all the filtering mode combination and output modes. Some new feature of this release is that it supports even multiprocessors, and it supports even kernel mode code tracing. As I have told, you can use the processor trace to trace even kernel software without any problem. In the developing of this driver, we had overcome a lot of problems. Like one of the most big problems are the mapping of the PMI interrupt, because there was no documentation at all for how to do that. And even the multiprocessor, because you have to manage and you have to enable the processor trace once in each processor. Okay, let's speak fastly about the PMI interrupt. The PMI interrupt has been raised by the processor trace when our buffer is full. And to do that, we have programmed the table of physical addresses inserting this PMI interrupt request at the end of the buffer. How we can be able to manage that? When the PMI interrupt raise, we suspend the target process, dump the physical memory, and then resume. We had some problem in implementing this because, as you probably know, all the interrupts inside the x86 architecture run at a very high QL. And this is quite a problem because from that code you can't do quite anything. Even the user mode buffer, very fast even here. We have found a way to directly map the physical memory in a user mode buffer. And we do this in a smart manner. I think it's not, we respect the security boundaries, and we mapped only the log buffer, and that's all in user mode, and not in kernel mode. It's important because if you use a very big buffer, you have the problem that for the virtual address space. Now it's not a problem in 64-bit systems, but could be. Okay, here is where the things get interesting, because in version 0.5 we have been able to support the multiprocessor and multi-thread application. Each CPU has, we have implemented in that way in which each CPU has its buffer associated with it, and it's mapped in user mode. And we signaled a PMI interrupt where the buffer will be filled. But here there is a problem, because if we fired the PMI interrupt in the same way, the user mode application is not fast and is not able to detect which CPU has the buffer full in a real-time way, in a fast enough way. Then we have switched the implementation and implementing the user mode callbacks. I mean, our user application has spawned one thread for each CPU, and each thread registers a PMI callback function. In that way, when a CPU has the buffer that is full, call the exactly right user mode callback. Here we have tested that even in a real big multiprocessor environment, if we don't decode in real time the binary log to transform it in a human readable text, the performance are really good. I mean, we can't see some slowdowns or something in the traced application. Speaking in summary, we have overcome this problem, but the only problem that we had is managing a multi-threaded application, because as you already know, for a CPU point of view, a thread doesn't exist. I mean, the CPU executes some codes. That's not, the CPU doesn't know if it belongs to one thread or another one. Okay, if you try to launch Calc, the standard calculator in Windows 10, you will find that it's not a standard process. It's a new app container process that spawns another process. This is an example of the increasing complex of even the standard process that spawn another process or multi-threaded. And here it could be a problem for our tracing purposes because of that. To overcome that, we can identify the paging information packets of each process and use the processor trace and instruct it to filtering by CR3. But we have a big drawback because the size of the log is huge. I mean, in that way you trace all the process that runs in user mode, all the loader code and whatever. And this is a problem. The second way to overcome this could be to register a process thread creation callback in kernel mode, and then trace only one process at a time. This solution is simple and it works, but sometimes it's not acceptable because, for example, some malware or some complex component, like for example Microsoft Word, require the interaction from different processes, and this is a problem. But we are researching a new way to do this because originally we would like to enable processor trace by each thread, using a thread construction. The thread is known only in software. Only Windows kernel know how to manage the threads. And our original idea was to intercept the thread context switcher code and save manually all the model-specific register used in processor trace to an area, and then restore back when the context switcher restore the original thread. When I was doing this, I was manually saving all model-specific register on an external buffer. But someone has pinpointed to me an existence of another very cool instruction that is not known by the research community, but is very useful. Do you remember the old push AD instruction in x86 architecture? Basically, what it does is that it pushes all the general purpose register in a user mode stack directly, only using one instructions. Now, in 64-bit environment, something like that doesn't exist anymore. But Intel has made this new cool instruction called xsave. The xsave is a new opcode in the MD64 instruction set that basically saves all some extended register, some register that belongs to the Intel architecture on a specific area. I mean, I have found that the xsave instruction can save MMX, SSE, AVX, AVX registers. And I have written here that what is AVX 512 because I didn't know the existence. The cool feature about the xsave is that it can save even the register that belongs to Intel processor trace and the new Intel memory protection extension. And this is very cool because using only one instruction we can save all the registers that belongs to the processor trace directly in a very, very fast manner, without any problem. If you open the Intel manual, you will find that to use this instruction, it's a bit complex because there is an xsave instruction that belongs only to user mode. And to set what to save, you have to set an extender control register in user mode using a new instruction that's called xsetBV. But to be able to save the model-specific register directly, you have to use another instruction. You have to use the xsave S. That it means xsave supervisor, and it's good to use it in kernel mode. Our driver supports completely the xsave, and it was very funny because when I have implemented this, I have found that the new Windows 10 context switches already implement the support of this xsave, but only for user mode. Our original intention was to find a way to intercept or divert the key swap context routine. That is the kernel mode routine that Windows uses to perform the context switcher from one thread to another thread. If we are able to intercept this, we can save all the model-specific register belongs to processor trace directly in an area, and then restore later. In that way, we can implement the tracing by thread. That is a completely software it lives in a completely software point of view. But we found some problem because, as you probably know, you can't touch in any kernel mode any kernel mode function in an official way using, for example, a nuke, I don't know, a code diversion or whatever, because otherwise PatchGuard will blue screen off your system. And we found that this way is not feasible in a public system. I mean, we can use our debug system. In a debug environment, you can do that, and PatchGuard doesn't run, and it's not a problem. But it's not a viable way in a production system. The second solution that we found is the usage of ETW. If you check the documentation about ETW, there is a way to intercept the context switcher, but we are still doing some research because the API are very complex, and we are trying to get if we are able to use in a legally way ETW to implement the thread, the trace by thread. Okay, another cool feature of the new release is that the driver now fully support the kernel mode tracing. We have implemented 11 new kernel APIs that you can attach to your driver, and you can use it manually to decide what to trace, to decide how to trace, and to do whatever from a kernel driver. But we were not happy with this because we would like even to implement the tracing from a user mode application. Then we have created some IOCTLs that you can communicate with our driver, and it's able to do kernel tracing directly from user mode. And to do this, we have overcame a lot of security problems. But now you can do that. From our user mode application, you can even trace the kernel code. I wrote here that in this way we are able to, for example, trace the loading or unloading of a kernel module, or even if maybe you are studying some IOCTL in a rootkit or whatever, you can even trace only the IOCTL code, because as you know, the IOCTL in kernel environment are processed asynchronously when a user mode application asks. Okay, some quick words about how to use the driver. As you can see, the code is quite simple. First of all, you have to grab a handle of our device. It's quite easy. The device name is named Windows Intel PT Dev. After that, you have to fill a data structure named PT user rec, that means a request. And then you have to ask the I/O manager to send the IOCTL to our device, specify the user request. After all, after this, the trace starts. You can decide where to stop the trace using another IOCTL. This is very important because if you close the application without doing that, it means that your processor is still tracing something. And this could lead a problem if you try to unload our driver, because the processor is not cleared. But the driver is able to detect this and to overcome this. But like it's a good practice to do that. For multiprocessor code, you can spawn a user mode thread directly without any problem. And then from the user mode thread, you have to to call the I/O manager to send the register PMI routine IOCTL to our device. That's all. Then you wait. You wait in an infinite loop. In infinite loop. And the only things to take care is that there is a parameter in the sleepx function that is named alertable or not. You have to insert true. In that way, every time the CPU buffer gets filled, the callback will be called without any problem. Okay, now it's time for a demo. I don't know how much. We have to be very fast. Okay, I have prepared a demo for you. Okay, you can see. Okay, as you can see here, there is the code of a very simple application. It asks only some question to the user. Let's try to run it. No kernel trace. Target process is our simple application.
Andrea, you can see here.
Ah, yeah, right. Okay, just a moment. How many CPU? At the beginning, let's do one, only one CPU.
He's asking you to increase the font size.
Ah, okay.
And you can probably just mirror it since we switch.
Yeah, I think that it's better, but...
So while he's setting this up, I'll recap a little bit about what he just went over. So our new driver, when we presented it last year in June, all we had shown is the raw capture of the binary trace. And so those packets of taken, not taken, taken IP, and timing was all that we had available. So we had to figure out how to decode this, and he's going to show you tracing in different modes and visualizing it in IDA. So.
Okay, can you see now? Okay. Let's do in the beginning for only one processor. How many recon conferences have you attended, guys? Let's say 3? Let's try with 3. Okay. The application has ended saying you are on a good track. That's it. Let's exit and try to open the executable using IDA. Okay, here there is the code. Our goal is to trace this software. We have developed a IDA plugin that does this for us. Let's feed it with the text log. Wait a moment. Okay, an exception. But as you can see, this is exactly the code that it has run. The exception was not voluntary, of course.
And so we use a library from Intel called libipt. It's open source, and it provides the decoding of the binary trace to a text file that we're parsing in the plugin for right now.
Okay.
Later we'll integrate the decoding within the plugin.
Okay, now I would like even to show you the same, but using multiprocessor environment. Let's see, where is the part of my process? How many processor? 4. And now let's say 8 conferences. Okay, the results are different. And you can see in the summary, each processor has its own buffer with different number of packets. Okay, it's this dump. As you can see, there are different binary files and text files for each processor. Now we'll increase the font size. Just a moment. Can you see, guys? Yeah? As you can see, this is a CPU number 1. It has all the packet, the taken, not taken, and the page generation enable and disable, because the context switcher of Windows switch to different thread. This is one CPU, but for example, if you are lucky, we are not lucky, there is even some logs that are quite clear, because it means that the Windows has executed this executable only for a small period of time. This is not the case because luckily the context switcher that's run for each different CPU, but sometimes it happens that even the log for one processor is empty. And this is our implementation.
Can you pull up one of those text files again?
Okay.
I just wanted to point out, so when you read these text files, you can see that For indirect branches and return addresses, we actually get the full 64-bit target address. But if you look at like the TNT packets, those are indicating whether or not a conditional branch was taken. So they only store a single bit that determines whether or not you took the true or false branch. So you have to recover that later on and disassemble in real time to recover what the target addresses were for those conditional branches.
We have time. Yeah. I would like to show even an experimental demo that uses kernel tracing directly for user mode. For this demo, I have chosen an ACP driver, not for a specific reason, because it was randomly chosen. And I have found that the system calls this interface a lot of times. Let's try to do even this, to take even those dump. The Explorer has been blocked. Amazing. Okay. Let's say yes, acpi.sys. Let's say go. Number of process of CPU, like just one for this time. Okay, it asks, I'm tracing. Do something and then stop me. I do, for example, some movement on my PC. And then at a point of time, I will say stop. In this time, we were quite lucky because, as you can see, the processor number 1 has taken some packets. Let's see what are those packets. Okay, as you can see, there is not so a lot of time, a lot of things registered here, but something has been taken. Let's try to use our plugin to be able to trace what. You can see this is the code of ACPI. Unfortunately, I have no symbol about this because it's an in-flight release of Windows 10. But let's try. Okay, the plugin has worked. You can see now because the driver entry has never been called. It has been already called when you have switched on your system. But if you see the log, there is a lot of time called this special function. That could be an IOCTL or whatever. Let's try to go. Yes, this is an IOCTL. You can see. Just a moment. I will. This should be blindly, without knowing anything about the interface of the driver. We can probably say that this is an IOCTL because the code is executed a lot of times. Because for the color is darker, and it means that the CPU has executed this function a lot of times. As you can see, there are traced all the branches. This is. Come on, because maybe it's not taken. And you can see there is the branch, and all the branches are traced. And that is the demo about the kernel tracing from user mode. From kernel mode, if you develop your driver, you are even be able to trace the driver entry or driver unload routine. I can show that right now because first we don't have time, and second my computer is switched on in a release environment. Because for doing that, of course, we can't use a signed driver. But it's feasible. If you do that, if you write your kernel driver and you sign your kernel driver, you can do whatever you would like. Okay, let's return back to the.
So now we'll switch.
Ah, okay, yes.
Yep. So to recap, the driver now supports kernel tracing and user mode tracing. You can filter based upon the CR3, so a single whole process. You can trace the entire kernel space, or you can isolate ranges of contiguous IP and you get up to 4 different ranges. So now I'm going to demonstrate this in a practical real-world scenario inside of AFL. So we have this fast tracing engine, and you'll see some performance numbers that are real world here, but in the manuals, they are targeting a 5 to 15% trace overhead for the entire system. So per core, you should be able to trace both kernel mode operations and user mode operations for only 5 to 15%. And I'll actually be able to show you that and how that works.
You don't have
I'm
the
sorry.
video.
Yes. Oh, I'm sorry. That will help.
It's that one.
Yes. Okay. So how do we use this and apply it for vulnerability discovery? So who here is familiar with American Fuzzy Lop, has used it? We have people who do fuzzing in the crowd. Okay, a good portion here. So in the last few years, we've seen an evolutionary jump in fuzzing technology. Basically, we've gone from using dumb fuzzing or grammar-based fuzzing that wasn't able to determine whether or not the samples that were being generated were useful, to applying a new technology or engineering an older technology into something that's performant enough to be used. And we call that evolutionary fuzzing. So we take the idea of dumb fuzzing mutation and we combine it with the ability to collect a feedback signal using code coverage. And then we assess the fitness of that new randomly generated input against the entire lifetime of your fuzzing cycle. And so basically what we can do is we can look at this code coverage information, determine if this newly generated input actually gets us to a different part of the code, and if it does, then we'll introduce that into our entire pool of samples and continue to mutate and fuzz those as we go. So over time, we're refining our set of inputs and we're building a corpus, and each one of those inputs exercises a slightly different part of the code. And in effect, what we've seen is the last 3 or 4 years since this has been available, this has highly optimized your compute time when it comes to doing dumb fuzzing. And so the last couple of talks I've given have focused on this technology, and so I encourage you to go look at previous slide decks, which are on the Recon website or my website at moflo.org. But basically, through researching this, I've resolved that the main things that we need to effectively deploy this technology is we need a fast tracing engine. And of course, that was the inspiration to look into Intel Processor Trace, because the promise of 15% overhead against closed source binary software is pretty incredible compared to the technologies that we've had available before. Previously, hardware tracing is not new to Intel. Since the P4, there's been the ability to do hardware tracing. There's mechanisms called branch trace store, BTS, which works in a similar fashion, but was not designed in a way that was optimized. It didn't write to physical RAM. It polluted your cache and things like that. So we saw a massive slowdown. And then you have another option, which is called last branch record, which is only 32 registers in modern processors, and those only give you the last 32 branches. So you'd have to interrupt every 32 branches to parse that and use that, and or you'd have to write a driver that flushes that out to a different cache and do other things. So while this isn't new, this is designed for the first time to be highly performant. Up until Intel Processor Trace, it was actually faster to use software-based tracers, things that would do dynamic binary instrumentation using Dynamo Rio or PIN or something like that. So now we have this fast tracing engine. That's great. We need fast logging, which is something that we get out of the design of AFL. AFL uses a Bloom filter that allows you to quickly look up whether or not you've done the same code coverage. So instead of parsing a text file or binary file that's just a list of addresses of basic blocks consecutively, we actually parse that in real time and fill a Bloom filter. So you can just check to see if this 64K of RAM is identical to another 64K of RAM instead of doing a comparison of each address. And then through some of my other research, there's been other attempts at evolutionary fuzzing starting about 2004 or 2005. Jared DeMott did some of his PhD research on this, and he had something called the evolutionary fuzzing system. But it was based upon basically the BTS record or debugger breakpoints, so it was quite slow in its tracing, and then it was also over-engineered trying to incorporate too much of the research that's in the evolutionary, like biology side of things. So the key is to have this fast tracing engine, efficient logging, and to keep the analysis to the minimum. So in 2013, Michael Zaleski, who's contributed a lot of great stuff to our industry, produced the first performant open source evolutionary fuzzer called American Fuzzy Lop. It uses a pretty comprehensive list of types of fuzzing strategies, whether it's bit flipping, byte flipping, D-word flipping, and so on, crossovers, and various types of mutation. Originally it used block coverage via a plugin, or a post-process of the GCC compilation. It would compile your code to assembler and then annotate the assembler to add callback hooks at every basic block entry point. And then that's through that modified source code, that's how you got your code coverage. And then, as I mentioned, he takes those edge transitions, basically shifts and XORs them together, and then increments offsets into this Bloom filter or bytemap that is basically able to track, whether or not you've seen this edge before. Now, you can't get out what those addresses were originally because it's simply an offset into this mapping, but you can very quickly look up, have I been here before? And that's all we care about as far as whether or not to keep that sample. And then, of course, it was written on top of the POSIX API, so it wasn't Windows compatible out the gate. The benefits that it has, it tracks edge transitions and not just block entry. It uses the Bloom filter. It had a fork server built into it. So basically, after your process has initialized, it waited until all your libraries are loaded and all the linking and everything is done. And then once you get to the parser code, then it would fork. And so you skip all that initialization time, which is an optimization. And then, very importantly, he introduced persistent mode fuzzing, which is an in-memory type of fuzzing where you're not exiting and recreating the process every time. You're giving it a pointer to a function and the number of arguments to that function and saying, okay, once you exit this section of code, start over again and take our new inputs as inputs to this function. And so that also reduces the amount of code that you're tracing and executing down to the minimal points as an optimization. And then, importantly, you can use this to build a corpus on open source software. It's very fast, and so you can use those as inputs into your pipeline on maybe slower or more heavyweight analysis on other types of fuzzing. So the way they do their tracing is every block gets a unique ID. The edges are indexed in that map. It creates that hash using the shift and XOR, and then we increment the map. So this was great. I was looking into this and how to optimize this and bring this to the Windows platform. Obviously, we can't use source code instrumentation for the majority of the software that we're targeting, so we needed something that could do binary targeting. And so this seemed ideal versus the other options of using Pin or Dynamo Rio and so on. And so last summer, we decided to start looking into this. Well, around that same time of my talk at Intel or at Recon last year, Ivan Fratrick from Google, I think he's Project Zero or Google Security, released WinAFL, which was a port of Michael Zaleski's AFL to Windows using Dynamo Rio as a backend. Are you guys familiar with Pin or Dynamo Rio? They're basically loaders for your program, and as you visit each new basic block of code, it caches that and allows you to modify it in real time. So it's a kind of heavy. Valgrind works the same way if you're familiar with that. So it was using that as a backend. It's really cool. It works. It was like the first thing that you could just go download right now and start fuzzing Windows GDI in 5 minutes. Beautiful. The biggest thing that's allowed it to be performant is that it uses this persistent mode where it doesn't exit the process. So these loaders like Pin or Dynamo Rio, they have to disassemble your program to instrument them. So he was able to, and I did some experimentation on trying to do forking in Windows previous talks, and it turns out it's just a real pain. So using persistent mode, you get things like you don't have to worry about ASLR because you're not exiting the process. And you don't have to disassemble the process every time because you're using that code cache. So WinAFL turned out to be pretty well engineered. And basically, you can tell it how many iterations to persist, like, maybe do 1,000 iterations, and then go ahead and exit and restart the process so that we can, if we have any memory leaks or we're not quite cleaning up properly, we can just handle that through delaying the restart. Now, persistence is key because every time you load this in the DBI, it's going to disassemble it. So if we were to just do it every time, we'd get 2 executions a second on this GDI plus demo I'm going to show you. If we persisted 100 times before we restart it, 72 executions a second, and so on. It reaches its ceiling somewhere around 1,000 or so iterations. So we've now integrated our Intel PT driver into WinAFL as an alternative tracer engine. And now this brings some problems, because the reason I had him show you the text version of that dump was that we don't have all of the addresses in the log file. So we have to recover some of those along the way. We don't have persistence mode working quite yet, unfortunately. I've done some experimentation here. It's around the corner. By the next time we present it to Hack in the Box, this will be available. I'm building my tooling on top of Alex Ionescu's great work from last year at Recon on the application verifier hooking system. And so basically, as it is, using the IP filtering mode, so you can specify up to 4 DLLs that you want to trace, or 4 modules or any address ranges in your process that you want to trace, and so on. The current status now is that we do accurately decode the full trace, so doing disassembly online and using cache for the control flow graph that you recover. So I first look to see if we've already resolved what this upcoming conditional branch is, and if so, then it's a quick index. If not, I have to disassemble forward to determine the targets for the conditional branch and then store those in a structure. The edge and source destination are recorded as expected, so we're not reduced to basic blocks. We actually do get the edges. And I'm currently just using create process, so we're doing this iteratively rather than forking or persistence mode yet. So in order to determine the performance of this tracing mechanism, I first made a dummy looping benchmark. So basically, it was just creating the process and waiting for it to exit. And so we get our kind of maximum bounds on how many iterations we'll be able to execute with this sample. In this case, I found that we could get 85 executions a second without doing any tracing. We're just generating the fuzzer input and running it without anything like that. We're not parsing the log file. We're not doing anything. So once we enable the tracing, that was reduced to 72 executions a second, which is right in that sweet zone of 15% overhead that Intel was promising for this particular sample. So parsing the log file was an additional 22% overhead, so now we're down to 55 executions a second. And I'll demo what this all means for you here. So we'll compare it to I'm going to show you, so we're going to fuzz GDI+. This is an experiment that comes with the WinAFL out the gate. You just pass it some image files, and it uses Windows to render them without rendering to the screen. And this is a live demo of that working. So currently, this is using Dynamo Rio and persistence mode with the maximum number of iterations possible. And we see that it's getting 127 executions a second. The lighting is not good here, unfortunately, but hopefully you guys can see that a little bit. I can increase the font just quickly here. So yeah, so what we're looking at here is this number specifically. So we get 126 executions a second using Dynamo Rio versus GDI. So let's see how our Windows PT driver performs in comparison. Oh, sorry, that's me decoding the log here. So let's redirect that out to null. Okay, so we're seeing with that overhead of the 15% for tracing and then the additional overhead of 22% for decoding, this will creep up a little bit, but we're only getting about 40-something executions a second. That's a little bit disappointing. We're hoping to see a little bit faster. Now, you have to keep in mind, again, that this is just iterative tracing. We're not doing in-memory fuzzing. So once we get to doing in-memory fuzzing, this number will increase significantly. However, this is not the end of the story. I originally was doing all my testing against their setup with the GDI Plus wrapper. And as you can see in my command line here, this is tracing only the Windows Codex DLL and the GDI Plus DLL in the process. So I made another demo in order to compare the performance, and this time we'll trace libpng using WinAFL. And so this is just libpng statically compiled into a small harness that will just load a PNG file, it'll fuzz it, and then it will fix up checksums, and then it will parse it through libpng. And we see that the performance becomes quite abysmal, actually. So this is the Dynamo Rio. That's expected. But we're seeing only 0.5 executions per second. So this is quite slow, obviously. This is not where we want to be. And this is because, since this is statically compiled, all of the code involved in libpng, including the encryption or compression and things like that, are included here, which causes some issues in the Dynamo Rio backend. Now, here's the fun part. We have a constant overhead when we use Intel PT. So using Intel PT, we can see that we're back up in that. This will creep up to about 55, 60 executions a second. So instead of being only half an execution a second, this is 100 times faster than the Dynamo Rio backend. And this is doing the full code coverage tracing, finding new paths, and so on. So, so with this engine, we've done 100 times performance increase depending on your target application. And this is not specifically chosen. This was just randomly. I had this fuzzer laying around and used it as a demo. So yeah, so that's my demos for this plugged into WinAFL. Thank you. And so just some closing remarks now. Number one, all the code that we've written is already open source or going to be open source. We're on GitHub/Intel PT, real simple. The driver is already there. I actually have a pull request from Andrea from last night, so the latest version is on GitHub. It'll be merged tonight. The WinAFL needs a little cleanup. I was up till 3:30 last night making my final preparations, so that code will be up next week. And then we just have a few more things that we need to address, but obviously, we see that code coverage is being finally harnessed to make our fuzzing better. We can load this information into IDA to do our analysis of crash or of malware or whatever it might be. And using the hardware-supported tracing engine, we don't have any issues like you would have with other software-based instrumentation and hooking engines. Once one of our future plans is to get this into a hypervisor so that we can trace the guests inside of a hypervisor, and then your malware tracing will be basically unobservable, and you won't be able to disable it in that method. There are capabilities of deploying Intel PT to trace things like SGX mode and SMM and BMM, and those are kind of future areas of work. And then also, my end goal is, of course, to get this fully supported with persistent mode and everything as well. One thing that we need to do as part of that is to finish the ETW-based thread context switch awareness, because we need to separate these logs out into a per-thread instance. Otherwise, you have to use the timing information to determine where the synchronization is between the threads, and that slows down the parsing a lot. So our goal is to get the logs individualized before you do your parsing, and so you only have to parse the thread that you care about that's doing your file or network I/O. And did you have any further comments on the solutions?
Just wanted to say that the new version that we are going to release already support the Xsave feature, and if you download it, you can test it directly, and it's quite a cool feature, at least in my opinion.
Okay, so you can get this code, and you can reach us on Twitter, and thank you very much. Hopefully, I think we might have a minute for questions. We're just on time. Yes.
Hey, thanks. Can you trace inside the virtual machine?
So currently, there aren't any hypervisors that currently expose this and virtualize this. So, for example, in the other hardware tracing modes, the hypervisor has to virtualize the support for writing to those MSRs. This does exist, like, for example, in VMware using the BTS mechanism, but Intel PT is rather new, so there aren't any hypervisors that are available yet. So we are either going to have to modify Zen or KVM, and we've been actually even just today talking about perhaps being able to trace the entirety of the hypervisor and then later on pull out only the user mode processor kernel threads that you're interested in. So currently, no, but absolutely we'll continue working on this until we get there.
Thanks.
Yeah, and I know that that will hopefully be applicable for Cuckoo Sandbox. So, were there any other questions? No? Okay, feel free to grab us. Thank you very much for your attention.